Last time, I said howdy. This time, we're just going to jump straight into it. No BS, let's go. The motivating example for the Chapter 1B lecture video is a graphical display of data. The focus of this lecture video is specifically going to be on graphical displays of data values and what to do with them. So here's something that every student should be able to relate to: letter grades. No matter how good or bad of a student you are, the letter grades that you earn in courses obviously have a big impact on your GPA, your major, and what you do beyond that. Now, of course, what you're learning should be the most important, especially in this course, given that this is a prerequisite for many other courses. So it's important that I do a good job teaching you these things. Even then, letter grades are nonetheless very important to students, and being able to look at them and digest them and figure out what information to make of them or any other data values is very important. These are letter grades across many semesters for a course called Math 3356, Quantitative Theory of Interest. It is a course that some of you are going to take after this one as a part of your major, depending upon your specialization. And the material you learn in this course would be very important in that one. I've taught the course before. Many other faculty members within our department have taught the course as well, such as Jihol Park, Abu Taleb Shirvani, and Alex Wank. And they've all taught the course and done a good job doing so. It's usually offered one section per semester, but let's suppose you were looking to enroll in the course and you were concerned about the possibility of getting a professor that just gave everybody an F, because you wouldn't be learning anything in there. And given how important this course would be to your degree, much as we might like to get a bunch of free A's, that helps in the short term. But if it's a course that matters for your degree, your specialization, and perhaps your job, learning is much more important. You'd like to learn and get an A, but you definitely do need to learn. Again, if it's just some random course for some general education thing that you probably only care about the letter grade, but if it's something for your major, you really do want to learn as well. And so these types of things can help you. Taking all those letter grades, semester by semester, section by section, and putting them into a display can really help you figure out which professors might do a good job of teaching and assessing you whilst also being fair. If you're wondering where to find this data, if you go to the MyTech portal and you scroll down to Explore Course Options, there should be an option you can click for grade distributions. Hopefully you find that to be helpful for you in your time here at Texas Tech. So you might look at this display, and we'll do a lot with it this lecture, and ask yourself, how do I construct this? How do I decide to use this display? Why not a different display? And how can I convey this information to be meaningful to somebody else? So let's talk about that. In order to get these percentages, we have some definitions. And so, of course, we're going to start off with some definitions like I promised. So here we have relative frequency and percent or percentage frequency. Relative frequency, very simple. Take the number of times something occurred in your sample and divide it by the sample size. So for example, if we have 19 people in this table saying they prefer Coca-Cola, 50 people total, the relative frequency is 19 out of 50. Your percentage frequency is equal to the relative frequency times 100, and then throw a percentage sign on at the end. So we add 19 out of 50. If you multiply that by 100, you get 38. Throw the percentage sign on the end, so we would say 38%. That's it. There's nothing else to it. Nice and simple to start. And you'll find with pretty much every single lecture video that we do, we start with the easier concepts first and gradually move our way up. If you need another moment to get those definitions written down, you can always pause and do so. And again, if it's the in-person section, of course, we would take time in person as well. For the rest of you, we can get immediately into some practice. So compute the relative and percentage frequencies for soft drink consumptions. You might look at this and think, well, this looks pretty easy. That's because it is. It'll start off easy and it will ramp up. So if you want to take a moment, go ahead and quickly do that practice and hit play when you're ready to continue. So Our relative frequency, you can put it in decimal or fraction form. Coca-Cola, 19 out of 50, 38%. Diet Coke, 8 out of 50, 16%. Dr. Pepper, 5 out of 50, 10%. Same with Sprite. And we keep going on and on. Your percentage frequency, you just throw the percentage sign onto the end. That's it. Nothing else to it. Now, I know some of you might look at the survey and say, bullshit, I don't like Coca-Cola. We all like Dr. Pepper. Screw your Coca-Cola, get it out. It's just a survey. Not making any statement on that. It's just a survey. You're sometimes going to get interesting results. I don't comment on those because I do not drink soft drinks. So, there's really nothing else to that. Relative and percentage frequency are very simple and straightforward to compute. You might say, fine, why do we talk about them? Because the relative and percentage frequencies help you define many of the remaining displays that we're going to go over for this unit. So, let's get on with it. So, we have histograms and bar charts. Histograms deal with quantitative data values, whereas bar charts deal with categorical data values. This is a distinction that can get a lot of people tripped up. And the reason why is because they both have bars. They both use bars, and those bars are all next to each other. So, when we're constructing a histogram, we need to decide how wide we want each bar, or in the case of histogram, the histograms bar, to be. To do that, we have something called the class width. The class width is equal to the largest data value minus the smallest, also known as the range, divided by the number of classes we want. This means the width of your rectangles will depend on how many rectangles you want to have. In this class, we will clearly define how many rectangles we want to have. In most cases, you'll already have your histogram. Thus, in the case of this frequency distribution, some people get audits from the Internal Revenue Service, IRS. Who knows why? Sometimes they're not paying their taxes. Other times they're doing some, shall we say, illicit behaviors. Maybe you're doing the, I don't know, right drug in the wrong state, or the wrong drug in the right state. Who knows? Just depends on whatever laws we came up with. And your taxes don't quite line up with what the government expects. Now, of course, the government knows how much you're supposed to pay, but they want you to figure it out. Regardless, sometimes there are audits, and so we have a frequency distribution for audit times. And so with these audits, we can construct many different displays of them. So, which displays might be best? The answer is, like with most things in life, it depends. Some displays will be better for some circumstances than others. It also depends upon who or to whom you are presenting the displays. Some people are going to prefer histograms. Some people prefer the bar charts. Some people don't know the difference. Some people just like their nice and simple pie charts. Some people want dot plots, line charts, you name it. Some people have no idea which one's supposed to apply where. Some people think they're all the same. So let's talk about all these different types of displays, because these are ultimately the bulk of today's lecture. So, and again, key point there, histograms for quantitative, bar charts for categorical. So, here we have our bar chart. And this bar chart is of the soft drink preferences. You can put it in frequency form. You can convert these into percentages. That is fine as well. Ultimately, part of that just comes down to personal preference. Because some people cannot look at these rectangles and know how much those constitute. Some people are not mathematically literate. You all are, of course. And so this is a simple bar chart display. You just take your frequency, percentage frequency, make the bars proportional to that height, and you're good. Nothing too crazy there. On the other hand, with the audit times, you might have something called a histogram. All these rectangles nice next to each other. And in this case, we chose to have 5 rectangles, and so a width of 5 each. You might say, not wrong, 4 each. Don't forget, you have to include the boundary. So if it's 10 to 14 days, that's 10, 11, 12, 13, 14. So 5 possibilities. 15, 16, 17, 18, 19, 5 possibilities. Technically, the width is 5 days here. And then, of course, you have your frequency. Much of it is more so just a difference in terms of, well, terminology. However, if we look at this histogram, suppose we took a line and we drew a line right down that peak. The left side doesn't look like the right side. It does not look symmetric. And the reason why is because this histogram is skewed. Skew is when we have one tail instead of 2. So many of you might be familiar with what's called the bell curve. Looks something like that. Now, that's not perfect, but you get the idea. So if we drew a line right down the bell curve, both sides are roughly the same. It's roughly symmetric. On the other hand, this histogram that we have up here, if we drew a line like this, it doesn't have 2 tails. We got one tail and it's running off to the right. So, we would say this histogram is skewed right. The direction of the tail is the direction of the skew. The significance of the skew is how far away that tail goes from the peak. So suppose the audit's ended there. We didn't know, but let's suppose it's like that. So here's our tail, here's our peak. It's a decent bit of a ways away. On the other hand, suppose the tail was like that. Tail's running off in the middle of nowhere. That time, it would be significantly skewed. So if you wanted an extremely clear example, let's remove this bell curve right here. I'll go up just a little bit. Here's one right here. And here's another. In the case of the second one, this tail is just very far away from the peak. It's going off in the middle of nowhere. That is very significantly skewed to the right. This other one, like with the histogram, is also skewed to the right, but not by a massive amount, so we'd say slightly or somewhat skewed. At this point, you might ask yourself, fine, what flips a tail from being slightly skewed to significantly skewed? The answer to that is subjectivity. In this class, I can promise you the significance of the skew will be very, very apparent and there won't be any gray area. So you would have an example like this. You might not have an example like this, where it's not immediately clear. I promise you, whenever you're asked about skew in this course, the direction of the skew and the significance of the skew will be very, very clear. So we talked about the right skew. What about the left skew? The left skew is just the opposite. So here you can see the tail goes off to the left. And in this one, you can see it goes very far off to the left. So the first one was slightly left skewed, whereas the second one is significantly left skewed. The part that is very important, the part that you will want to have written down, is this box. Your skew is in the direction of the tail, and the significance of your skew is how far away your tail goes from the peak. So, now that we've talked about the skew, let's continue. We also have a dot plot. And as you can see, the dot plot also makes the skew pretty apparent. So, here, It's technically a bit more flattened, but your peak is right in here. Your tail is not too massively far away from it. It's a decent bit of ways, but not massively. A dot plot is, as implied, a bunch of dots on a line, where these dots are your individual data values. Nothing too crazy here. You don't see dot plots all that much. And the reason why is because a dot plot is essentially a goofier form of a histogram in that example. So you might sporadically see dot plots, but what's more common is what's called a scatter plot, which we'll particularly talk about all the way in chapter 13. Scatter plots are the far more common form of the dots being all over the place. So here's a dot plot, if that tickles your fancy. And then everyone's favorite chart, the pie chart. Nice, simple, easy to understand. Even a complete and total bozo could understand a pie chart. And in fact, there will be a pie chart question on your Unit 1 test. Should be a freebie. In all my time teaching this course, there was only one semester where somebody didn't get the pie chart correct. It was incredible. It was a momentous experience. Somebody didn't know what a pie chart was. But you'll know what a pie chart is. Because quite literally, it looks like a pie. Or maybe a pizza, I suppose. Could be a pizza chart. Hey, if history was a bit different, we might be calling this a pizza chart. I would say some food for thought, but that's a pretty bad pun. Regardless, here is your pie chart of the categorical data that we had for the soft drinks. Usually you have pie charts with the bar charts, so they pair together, and then your dot plots with the histograms. Usually, when you're dealing with categorical data values, you'll see a pie chart more often than a bar chart. And when dealing with the quantitative ones, you'll see a histogram much more often than a dot plot. So, on the test, I'm going to give you a chart, a series of charts. And you're going to have to identify which type of chart it is. For most of you, it should be a cakewalk. Or, if I may be permitted an absolutely terrible pun, easy as pie. Ha! I'm funny. Sort of. But regardless, you'll have 4 answer choices: bar chart, histogram, pie chart, dot plot, none of these, whatever. And you'll need to pick which one it is. In the case of the charts, there's no partial credit. Because if the answer is bar chart and you pick pie chart, I don't know what to tell you. Other than the fact that you should go double check what a pie is. And likewise, if the answer is dot plot, but you pick a histogram, then I don't know what to tell you. So these should be relatively straightforward. Should be some relatively easy points. And you might look at this and think, oh, well, this is pretty easy. I'm pretty sure I can tell the difference between a histogram and a dot plot. Don't forget, the average person is not as good at math or stats as you are. Even if you think you're bad at math or stats, don't forget there are a lot of other people out there who don't even know what a pie chart is. So with that, let's continue on. We now have what is called a cumulative frequency distribution. So here we have some more definitions, because we mainly need these to introduce the ogive and computations. Now, at this moment, you might say, hold on, Professor, where are all the examples? We've only gone over one example I can work out. Where are my examples? Don't worry. The entire back end of the lecture video is just going to be examples, and there will be a lot of them. So with a cumulative frequency distribution, like with the frequency distribution, which is a table of all of our frequencies, but this time it's cumulative frequency. Here's how cumulative frequency works. It's everything up to and including that point. So for example, suppose we're talking about letter grades for this course. You have A's, B's, C's, and F's. The cumulative frequency of F grades is anything less than or equal to an F, which is the same thing as just saying an F. If I asked you for the cumulative frequency up to the C grades, that's everything less than or equal to a C, which is the F's and the C's. If I said everything up to and including the B grades, that is going to be the F's, the C's, and the B's. And then finally, the A grades, everything up to and including the A's will be, well, everything. The F's, the C's, the B's, and the A's. I promise this is not a Sesame Street show where we're talking about the alphabet. Notice you can do a shortcut. If you compute the cumulative frequency of F's, all you have to do to get the cumulative frequency of C's is add the C's. To get the cumulative frequency of B's, just add the B's. And for the cumulative frequency of A's, you then add the A's. There's a web work problem like this, but pay particular attention to whether it's just frequency, relative frequency, or percentage frequency. These are computed in essentially the same way as with regular ones. Percentage is just relative with the percent sign on the end times 100. Frequency is what you have. Relative is making that out of everything. When dealing with cumulative, we usually, not always, but usually are using cumulative percentage frequency. And we display this through what's called an ogive. So here we have this ogive. And suppose we have some prices of fruits. Let's suppose these are fruit prices. These are some organic fruits that are expensive. You're in California and everything costs $400 million. If you're from California, you probably know exactly what I'm talking about. So, 0% of the fruits cost $0. We might wish they didn't cost anything, but tough luck. On the other hand, the cumulative percentage frequency of the fruits costing $5 is 30%. So here the line goes from 0, 0 to 5, 30. The $10, so up to $10 for the fruit costs, that's right here, is 70%, which is going to put us roughly in here. And so therefore, we have our coordinate pair right there. The $15 fruits take us up to about 90%. And so therefore we have our coordinate pair there. And then finally, once we hit $20, we've hit all the fruits. I don't know what fruit you're buying at that point. That's $20, but hey, you can buy what you want. So essentially the whole idea behind an ogive is create a series of coordinate pairs of, in this case, your price or input and the percentage. And we keep going. I promise that is not a face. It's just a 0, 0. And then 10 to 70, 15 to 90, 20 to 10. And so the idea is you take these coordinate pairs, you quite literally plot the coordinate pairs and connect them up with the lines. And that's an ogive. Nothing too crazy. It's just taking what you have and putting it in visual form. You pretty much always use ogives when you're trying to graph or display your cumulative frequencies, relative frequencies, or percentage frequencies. So, those concepts of cumulative, let's spend the entire remainder of the lecture on practice problems. So now there's a very important note I want to make here, and you're going to see this with all of the remaining lecture videos. The older lecture videos, technically speaking, which are obviously available to y'all for those that like them, are technically longer than these recorded and updated ones. The reason why is because those were directly from the in-person lectures. And when you're working an example in person, students will usually like some time to work on it. I don't think it's reasonable to expect somebody to get the answer to a hard question in half a second. Some people might, most can't. And so we'll spend some time in class going over those. Additionally, usually we'll allocate some time in class for students to write those definitions down. And so usually you'll find that the in-person lecture videos, like straight up from the in-person class being recorded, are a little bit longer than these recorded ones. It's the same material. Effectively, the main difference, aside from any updated whiteboards, is you have it paused, like you pause the lecture video to write something down or work an example instead of just having 5 minutes of dead time. So, here we have an example for relative and percentage frequency. So I want you to take a little bit to provide the relative frequency and the percentage frequency distributions. So you have one column for each. If you don't have the blank whiteboard in front of you, you can, of course, put it down in your notebook, or you can just pull up a calculator and do it yourself. For those of you that have the blank whiteboard, you can see how it works really well to work it out for yourself. Again, choose whichever you prefer, whichever is best for you. All right. So, let's go over the answers. So, in the case of growth in income, this is a fun objective, and this is a finance example. Again, most of the students are students dealing with business, finance, accounting, and whatnot. So majority of the examples will be business, finance, and whatnot. But like I said, we're going to ensure that we have examples for everybody as well. So for relative frequency, if we have a total of 26 funds doing growth in income, and we have a total of 137 funds, as indicated by that 137. In this case, if you want to compute it to be relative, it's going to be roughly 0.190. So roughly 0.190. In this class, we're going to round nearly everything off to 3 decimal places. Sporadically, you might see a 4th decimal place, but we'll usually stick with 3 decimal places. Now, for the international, we have a total of 42 of them trying to meet that objective. We have 137 total funds, meaning, and we'll do this to keep the formatting the same, that roughly 0.307 constitute the relative frequency. If you're wondering where these numbers are coming from, it's just from putting it into a calculator. So you do 42 out of 137. For our third fund, we have 20 specializing in mid-cap. You might ask yourself, what is mid-cap? Mid-cap, as is implied by the word mid, are the mid-sized companies. Many of these are in the S&P 500, which is another index. The Dow Jones has the really big cap companies. S&P has large cap, maybe a couple mid-cap. And then for the small cap, there's something called the Russell 2000. That one has a lot of your smaller companies and corporations in the United States. So you have the Dow Jones, S&P 500, and the Russell 2000. If you decide to manage any kind of a fund, maybe you go work for a hedge fund on Wall Street after your time here at Tech, you might have to decide between these objectives what you want to go for. And that's going to a certain extent depend on what your clients are looking for. What do they want to specialize the fund in? Are they looking for stability, guaranteed income, high returns? What are they looking for? Do they want exposure to international funds? Are they what you might call a tech bro? They like their GameStop? Or their AMD? Who knows? Just depends on what clients you have. Regardless, 20 out of 137 is roughly 0.146. For our small cap funds, many of which would be in the Russell 2000, there are a total of 37 of them. And we have 137 total funds in our sample, which means this is going to be roughly 0.270. Notice for a couple of these, we have a 0 at the end. That doesn't mean there are any more decimals left. It just means it round off to a 0. And then for technology, we had 12 of them, 137 funds total. And so in that case, it comes out to roughly 0.088. For percentage frequency, very simple and straightforward. We just multiply by 100. So multiplying that 0.190 by 100 will give you 19%. In order to preserve the full decimals, I'm going to include those as well. So with your calculator, technically speaking, it's going to be 18.987%. And so as you can see, if we move that decimal 2 places to the left, the 7 kicks the 8 up to a 9, which kicks the 9 up to a 10, which therefore kicks the 8 up to a 9. 42 out of 137 in percentage form is going to be 30.657%. 20 out of 137 in percentage form is 14.599%. Hit a space to keep the formatting. Our 37 out of 137 in percentage form is going to be 27.007%. And your 12 out of 137 percentage form is 8.759%. And those are your answers for the tabular distribution. There's a very important thing to note here. Sometimes your numbers might not perfectly add up to 1 or 100%. Sometimes they exactly will. Sometimes it might be 100.1%. That usually just means you have some small round off. If you only have small round off error of, say, 0.001, then you're okay. More of that is a problem. So if your round off error was 1%, that means you had a computational error somewhere. WebWork has a rounding tolerance of 0.001. So if you have a very tiny round off error, WebWork will be okay with that. If, on the other hand, the answer is 27% and you put 29%, that's a bit of a different story. So with that, let us continue. So, this one is both going to be a teaching and an example. Stem and leaf displays. You might say, wait a minute, you said we were doing all examples. You little shit, you're giving us another concept to work with. The answer to that is only sort of. So here's a stem and leaf display of some data values. Notice I put some rectangles around these. Why? Simple. If I take this stem and leaf display and I rotate it to the left, that might look familiar because it's a histogram. A stem and leaf display is literally just a rotated histogram. That's it. Nothing else to it. That's it. There really is nothing else to it. So if you're wondering what these values are, these are the leaves and these are the stems. How do you read them? Simple. 6 and 8, 68. 6 and 9, 69. 7 and 2, 72. And you can do this for all the ones in there. 8 and 0, 80. You can do it for all the ones in there. 9 and 1, 91. 10 and a 0, 100. Notice, though, we have 2 zeros. This doesn't mean we have a data value of 1,000. It means we have 2 100s. So if you see the same leaf repeat itself, we have duplicates of the data values. You can see we have 3 6s in here, so we have 3 106s. Here we have an 11 and a 2, so that's 112. Here we have a 12 and a 4, so that's 124. We have a 13 and a 2, 132, and then the 141. That's how you read a stem leaf display. Very simple. Your final digit, the singles digit, the ones digit, will be with the leaf. Everything else will be the stem. Sometimes you have so many data values in one 10-digit interval that you split it up in half. So, again, a stem and leaf display is just a rotated histogram. So that you know that, here is a practice example with a different stem and leaf display for data values. This one also highlights the importance of what we call cutoffs. A cutoff is quite literally your cutoff value for cumulative percentages. So for example, if I said less than or equal to 75, then 75 is your cutoff value. But whether or not the equal sign there can heavily impact your final answer. So with that in mind, go ahead and do parts 1, 2, and 3 for this stem and leaf display, which also gives you practice with cumulative frequency, cumulative percentage frequency, and we'll go over the answers. All right, so our first one, we have a 5 and a 5, meaning our first row has 55 and 57. Our second row, we have a 6 and a 2, so 62, and a 6 and a 3, which is 63. In the third row, we have a 7 and a 1, which is 71. We have 2 5s, which means we have 2 75s. In our third row, we have an 8 and a 4, which means 84. In our last row, we have a 0 and a 9, which means a 0 and an 8, which means we have a 90 and a 98. So there's part 1. Parts 2 and 3 are meant not only to be practiced with cumulative percentage frequency, but also with how the cutoff can change the final answer. So let's start with number 2. In the case of number 2, a B grade in at least my courses for Professor Bailey is a 75% or higher. If you have a 75, that's a B. So that'll be greater than or equal to 75%. So what percentage of the class scored a B grade or higher? Well, we have 2 people that scored a 75, and we have 3 people that were higher than a 75. So we have 5 people total. So 5 out of 10, which is 50%. But now, what about the third part? Let's suppose your professor is a poop head and doesn't round anything. So you had it exactly a 75. Not good enough. We're not rounding that up. So let's suppose your professor never rounds anything at all. So now let's suppose you have to be outright higher than 75.0. Now what percentage of the class has a B grade or higher? In this case, these 75s no longer count. Only the 84 to the 98 do. So this time we're down to 3 out of 10, which is now 30%. So when you're doing these problems, both in the web work and especially the test, pay very, very close attention, not just to what your cutoff is, but what the boundary on that cutoff is. Is it just greater than or less than, or is the equal sign also included? Because particularly when we get large data sizes, that equal sign can change the entire answer. And of course, in the case of college and schooling, you want us to include the equal sign because that means your 80s or 90s or 89.9 technically count as an A. And yes, you have an 89.9, I'll round that up, of course. So now with that, let's get on to the most difficult problem for the lecture. This one's going to take a good bit of deal, not just to work through, but to explain. This is the difficulty level that you will see on the test. And these ones also were, but particularly this final one will be as well. So if there's any example you work out, it should definitely be this one. So I will zoom in case you're unable to see it. Notice for this one, we have a lot of different questions, and it's phrased for everyone to be useful. For those of you that are particularly astute observers, you'll notice that these are the data values that made up our displays from the motivating example. So now we're taking the motivating example and doing a bunch of practice ones with it. And I hope that all of you, whether you're a business major, animal science major, general studies major, what have you, find this to be very helpful for your remaining time here at Texas Tech and any other universities if you choose to go to a different university after this semester. So with that, take some time to work on this. If this was an in-person section, usually we would allocate around 5 to 7 minutes to work on it. So go ahead, take your time to work on it, pause it, and when you're ready to continue, you can unpause, and we'll go over these many, many examples. So for our first one, for which section did the B grades constitute an outright majority of the letter grades, what we're going to do is look for half plus 1 for each section. So for example, for our final section, we have a total of 33 students. So half plus 1 is going to be 17. So are there at least 17 Bs? The answer is no. So it's not going to be the final section. 34, half plus 1 is 18. Only have 8 Bs? That's not a majority, so it won't be them. 23 for our middle section. Only 3 Bs. Half plus 1 would be 12. Not a majority, so it won't be them. How about 56? Well, half plus 1 would be 29. We only have 15 Bs. That's not enough. On the other hand, for our final section at the top, half plus 1 would be 26. That is 26 out of 51. That is a majority. And so therefore, it will be me for this one. So now for the second and third part, starting with the second, we're going to the left of our table, have 2 columns to show the computations for these. We're going to compute the percent frequency of A grades for each class, and then the highest percent frequency will be our answer here. So we're just going to call that off to the left here, 8%, and I'll make that a bit larger so it is easier to see. So for our first section, we have a total of 16 A's. I'll make this a bit smaller so it lines up better. Oh, it doesn't seem to want to, so we'll just do that. There we go. So for the first section, we have 16 A's and 51 students total. This comes out to be about 31.373%. Let's make the text a bit smaller so we have more room to work with. There we go. For our next section, we have a total of 56 students, and there are 17 A's, so 17 out of 56. And in that case, that's going to come out to be about 30.357%. For our third section, we have a total of 23 students, and we have 9 A's, so that's 9 out of 23, which is going to come out to be about 39.130%. Then for our fourth section, we have 11 students, 34 A's, and that is going to come out to be about 32.353%. For our final section, we have 17 A's, 33 students total. That's an outright majority of 51.515%. And so, the final section is the one where, on paper, randomly picking a student, the chances of getting an A would be the highest. And then finally, assuming that D grades are failing, we're to compute the relative frequency for each class and identify if there's any class where more than a quarter did not pass. So, we're just going to call this the fail. And you can use this as fractions. You can put it as a percentage if you want. I'll show it with the decimal here. But again, you can do fraction or percent or decimal. All are fine. For first one, we only have one student who had an F, no D's, so 1 over 51. And in that case, that's going to come out to be roughly 0.01961. For the next class, we have 13 total D's and F's. 5 plus 8, 13. 13 out of 56. I'll put the tilde there for rounding. And that comes out to be about 0.23214. For the next section, let's just keep this in line. For the next section we have here, we have 6 D's and no F's. So that's 6 out of 23, which comes out to be 0.26087. So there we have at least a quarter. Let's continue on to our next section. So here we have 4 D's and no F's, so it's just simply 4 out of 34, which is going to come out to be about 0.11765. And then for our final section, 3 D's and 1 F, it's 4 out of 33. And so that comes out to be about 0.12121. As you can see here, there is a section for which at least a quarter of the students failed. That is, they didn't pass. And that is our third section. These are going to be extremely similar in difficulty level and formatting to the questions you'd have from these tables on the Unit 1 test. So if you're unsure about what happened here, it's good to review it. So that way, you can ensure that you're good to go on them for the Unit 1 test. Those are the last ones for today's lecture. Hope you have a great rest of your day, and I will see you with Chapter 2.